Welcome to the Sophistic online documentation. In this tutorial we will show you how to carry out design checks for composite bridges. In this video we will first give an overview of the workflow and then guide you through the first step, the modeling of the structural system. We will introduce the workflow using a simple composite bridge with two spans of 16 meter length. The bridge cross-section consists of two main girders with transverse bracing at the abutments and at the inner support. The spacing between the main girders is 3 meters and the slab cantilever at each side has a width of 1.5 meters. Each girder has a structural steel section with a height of 1 meter. The flanges have a width of 450 millimeters. The concrete slab associated with each composite girder has a width of 3 meters and a thickness of 30 centimeters.
We have structured the workflow in the following main parts. In the sequel of this video, we will first create the structure using our graphical preprocessor SOPHI Plus. In the following videos, we then define the loads on the structure, then we do the analysis for the construction process, temperature and settlement, and the traffic loads. Then we do the superpositioning and create the design combinations. Using the combination results, we then do the design checks. Now let's start with the modeling of the structure.
Open the Sophistic Structural Desktop and create a new project. Choose a name for the file and select your code of choice. In the SSD, open SOPHI Plus, our graphical preprocessor. Here, we first will create the bridge axis. In the Systems tab, go to Axis, right-click and create a new axis. Give it a title and create it. And select a sufficient length. Here we will take 50 meters. That should be enough. Okay, you can see the axis exists now. Now we will also create secondary axis, which we use to define the position of the main girders and the limits of the slab in cross direction. Create secondary axis with an offset of -3, -1.5, (1.5), and 3 meters. In longitudinal direction, we create placements to define the start and end of the bridge at x equals 0 and x equals 32 meters, and at the position of the inner support at x equals 16 meters. The Eurocode allows to account for the reduction of stiffness at the inner supports due to cracking of concrete by using the stiffness of the cracked composite section at the inner support in the system analysis. The area where the cracked stiffness should be applied is between 15% of the span length left and right from the inner support. For this purpose, we define two placements at x equals 13.6 meters and 18.4 meters. To keep this tutorial compact, we will use these positions also as the border between the concreting segments in the span and the concreting segments at the inner support, And we place here also the change from the span cross-section to the cross-section at the support, which has a higher amount of reinforcement. Next we define the materials for the cross-section of the main girders. Go to materials, and as you can see we have already materials available but not the ones we need, so change the first material to structural steel of type 355. Change the second material to standard concrete of type 35, and the third material to reinforcing steel of type B500B. Furthermore, we need a second structural steel material which we will use to define the shear connection between the structural steel and concrete. So for this purpose, create a new material from design code, which will also be set to structural steel of type 355. Okay, then we have all the materials available, and now we can define the cross section. For this purpose, go to cross section, right click and create a new thin walled section of type composite. In the section properties dialog, you can give this section a name and assign the reference material, which here is already correctly the structural steel.
For composite girders that are usually part of an overall bridge deck and therefore dominantly act in uniaxial bending, we strongly recommend to suppress the rotation of the principal axis. This is especially important for girders that have different widths for the left and the right part of the concrete slab. Okay, what we also need are construction stages.
So create 2 construction stages. First here with number 10. You can also give this a name. We call it structural steel because this is the part where only the structural steel part of the section will be active. And then a second construction stage here with number 20, which then also includes the concrete, so is the full composite section. Then we click on OK and can start to define the cross-section in the cross-section editor. To define the cross-section elements, I will shortly sketch the cross-section parts. For this purpose, I will first create a point at the origin of the cross-section coordinate system, so at 0, 0, and then draw the cross-section using the AutoCAD line command. Now we can draw the thin-walled elements for the cross-section. We'll start with the structural steel, so create a thin-walled element of type structural steel with a thickness of 30 millimeters for the top flange. You should assign the correct construction stage, which is here already correctly number 10, structural steel section. Okay, so we create the first element of the flange, then the second. Note that we also can assign a name for this element to later be able to recognize it in the reports of the design checks. So here I assign FTL for flange top left, and FTR for flange top right, and then proceed with the bottom flange, which has a thickness of 40 millimeters and should also be assigned a name, so flange bottom left, flange bottom right. Okay, and then we create the web. We name it as such, and it has a thickness of 15 millimeters. Please note that we start here at the endpoint of the top flange elements and go to the endpoint of the bottom flange elements, so that these thin walled elements are all interconnected. Okay, that's fine. Now we can create the thin walled elements for the concrete slab. So just as before, select thin walled elements. We also will give a name, so concrete left here. Select now the correct material, the concrete. Assign the right thickness, 300 millimeters. And now it's important to select the correct construction stage, number 20, where the concrete will be active. So I create the left concrete element, now the right one, concrete right. Okay, that's it so far. For the calculation of the shear distribution in the cross section, it is important that the thin walled elements are connected to one another at their start, respectively endpoints. This connection is still missing between the concrete and the steel elements. To solve this, we define a shear connection of type dowel. We can also give it a name. And as material, we choose the structural steel material that we already defined for it. And note that we recommend to set the thickness of this connection in the order of magnitude of the web thickness. Also remember to assign the correct construction stage. So this is only relevant when the composite is active. So we assign construction stage 20. And now we create it and connect concrete and steel. And note that this element we will use also later on to evaluate shear forces to design the shear connection. A topic that we have not treated until now, also concerning the connection between structural steel and concrete, is that the top flange of the steel section is usually not prone to local buckling, as it is connected via headstock anchors to the concrete, and therefore we want to deactivate the C2T checks for these elements, and we can do this here by setting the boundary conditions for the C2T checks as deactivated. So we do this for the left top flange element and for the right one. Okay, then our cross section is almost finished. The only thing still missing is the reinforcements. I will first sketch its position. So we have one layer with a distance of 50 millimeters from the top of the concrete, and a second layer from the bottom with the same distance to the concrete edge. Now we have the position and can define the reinforcement using the line reinforcement command. In the span section that we define now, we will use a reinforcement with diameter 16 millimeter and a distance of 150 millimeters. We can also assign a title to be able to recognize it later. Here I give RT for reinforcement top. And it's also important, of course, to set the correct construction stage, so 20 here. Okay, I create the top reinforcement. And then I repeat this for the bottom reinforcement. So same amount here, and of course the construction stage. A point still missing is the definition of effective widths to account for the shear lag in the concrete slab. For this we use so-called non-effective areas to define the parts of the concrete slab that are not effective due to the shear lag. So first create a non-effective area at each side of the slab. Set it to be effective for all internal forces and also to apply to the reinforcements. Assign cross-section 20 like for the affected concrete elements. The size of the non-effective area, respectively its width, is not relevant yet, as we will adjust it in the next step using an axis variable to interpolate the effective width, respectively the cross-section, along the axis. To do this, we close the cross-section, of course save it, and then go to the bridge axis and create a new axis variable. Here I will name it. To this variable we assign the values of the effective width along the axis that I calculated previously according to the provisions of Eurocode 4. The cross section. Okay, having created the variable, we can reopen and import the created variable in the cross section properties. Now we can use this variable to define the size of the non-effective areas. For this purpose, click on Cartesian references in the sidebar and select a point that defines the inner boundary of a non-effective area. Next, specify the reference point for the horizontal and vertical distance. In our case, just click twice on the origin of the cross-section coordinate system. To link the horizontal reference to a variable, click on it and unlock the displayed dependency. Now you can enter a new dependency. We will use the feature to enter a formula including an axis variable and assign half of the variable BF. Repeat this for the non-effective area on the other side of the slab. Remember that we are assigning values in the cross-section coordinate system, so take care to assign the correct signs. The last point missing are stress points. For example, for the fatigue design checks, it is necessary to evaluate the stress ranges at certain points in the cross-section. For this purpose, we will, in the simple example, create two stress points, one at the position of the weld between web and top flange and the other at the weld between web and bottom flange.
For the evaluation of the shear stresses in the stress point, we recommend to position the stress points such that they can be clearly attributed to one of the thin-walled elements. For this purpose, I will draw an additional line that gives me that position. So, example here, taking an offset of 5 millimeters to be clearly in the thin-walled element describing the web. Okay, then let's create the stress points. Make sure to have the correct material assigned and also the correct construction stage. And you can also give a name to the stress point. Here I will use web T for top. Create the stress point, and for that at the bottom I will use the name web B for bottom.
Okay, now having finished the definition of the span section, we can close and save the cross section. Okay, now we have defined the span section, but as noted previously, for the analysis we want to set the properties of the cracked section at the inner support to account for the stiffness reduction due to cracking in this area. For this purpose we define the support section by cloning the span section and modifying it. So please open the clone section. We will change the name, and to set the cracked stiffness for the section we will use a concrete with reduced elastic modulus. You can directly create this concrete material in the cross-section editor by selecting one of the concrete elements and creating a new material for it. Here we will take the same concrete type as in the span, but reduce the elastic modulus. Please first set the stick here. This will make sure that the shear modulus is unaffected by our changes of the elastic modulus. And now we set the elastic modulus to a value close to 0 compared to this original value of about 34,000 Newton per square millimeter. I will choose here 300. Okay, let's create this material, and yeah, you see it's already assigned automatically. I click on OK and do the same thing for the right concrete element. Now we will make two further adjustments for the cross section at the support. First, we will adjust the construction stage where the concrete elements are activated. Remember, in the construction process we plan to pour concrete first in the span part and then in a second step do the concreting around the inner supports. For this purpose we create a further construction stage with number 30 in the cross-section properties. Okay, now we assign this construction stage to the concrete elements, the non-effective areas and the reinforcement. Yeah, you see, we should not forget the shear connection. And okay, now all the relevant elements have been assigned to the new construction stage. Now we can also make a check if we haven't forgot anything by trying to delete the now unused stage 20 in this section. I deleted, okay, it works. otherwise you should get a warning that it's already used, so we haven't forgotten anything. And now I will make one further change to the support cross-section. I suppose that we will need a higher amount of reinforcement here, close to the inner supports. Therefore, I select the line reinforcements and assign a higher reinforcement amount by setting here diameter 20 and distance 100 millimeters for the upper and the lower reinforcement. Then close and save the support section. Now we can create the beam elements for the main girders. Go to Structural Elements and select Line. In the General tab, assign Group 1, and in the Beam tab, select as element type Beam with reference axis and assign the previously defined cross-section 1. Then select for the creation of the structural lines the option Segment on Axis. And click on the secondary axis at the position at the left girder, so axis B, and create the beam elements, respectively structural lines, between all placements. Then repeat this for the right girder, so here at secondary axis C. We have now created the structural lines with cross-section 1 over the complete bridge length. However, at the inner supports, we want to have the support cross-section with number 2. So we change the cross-section of the corresponding structural lines in between these two placements here accordingly. I also have recognized that these two placements here are still displayed as support placements, as this, and this placement here. So I will make a short change in the placement definition to get a better visualization. Okay, now we can export the system from Sophie Plus and take a first look at the created beam elements. As you can see, we get two girders, respectively the corresponding beam elements, and you can also see that we have assigned the non-effective widths at the inner support and also the small non-effective widths at the abutments correctly. Next, we will create structural areas which we use for the load distribution in cross direction between the girders and also to connect the girders in cross direction. For this purpose, we first create a new material for these structural areas. So create a new material from design code, select the correct concrete type, here class 35. And now important, as we have the concrete already assigned in the definition of our beam cross sections, we set the self-weight of the new concrete material for the structural area to 0, otherwise we would have the concrete weight twice in the system. Concerning its stiffness, we will take measures later on using stiffness modifiers that I will introduce in the following videos. I also create a new reinforcement material Okay, then we can start to create the slab. So go to structural elements and select area, and now assign for the structural areas the group number 2 and the material 10 that we created previously for the area itself. So this is the concrete, and of course this concrete slab also gets reinforcement. Here we take the newly created material 11, and of course we want to assign the correct thickness, 300 millimeters, and then create the elements. As previously, for the beam elements we choose segment on axis and then create the structural areas between the secondary axes that define the boundary of the slab. And of course we want to have them between all placements. You can see the area elements are created now. Please check if the structural areas have the correct group number. So here we want to have group number 2 for the structural areas in the span that will or that belong to an earlier concreting stage, and the area elements close to the inner support we want to have in group number 3 because they will get concreted at a later stage, and we use these group numbers to assign a correct construction stage number later on. To check the system we can export from Sophie Plus. Take a look in the animator, and here we can see that the position of the area elements does not yet fit to the definition of the concrete slab in the beam elements. So these area elements are too high here. So to solve this we go back to Sophie Plus, select all area elements, go to the geometry tab, and there select an element alignment in positive local Z direction. Once again we export from Sophie Plus. Take a look at the system. Okay, now it looks fine. Okay, next we will create the transverse bracing. For this we define the corresponding girders in cross direction. So this we will do in the cross sections part. Right click and create a new standard section, a steel profile, select as calculation method Finwald. The material number is already correct. We will take a profile of type IPE 600, and to get the correct height we set the reference point at top center and the coordinates in Z direction at 500 millimeters. So yeah, you can see where this profile will get inserted.
Okay, now let's create structural lines for the transverse bracing. So go to line and make sure that we have group number 1 assigned. And as element type, we want to have beam with reference axis, and we choose the newly created cross section number 3. Okay, and then create structural line at first abutment, then same thing at the inner support, and same thing at the second abutment. Okay, fine. Then, as next step, we want to create the bridge bearings. For this purpose, we go to the cross members editor by double-clicking on placement. Now, as you can see in the cross members editor, we already have displayed the bridge cross section. And the first thing I would like to do here is to create a point constraint from the nodes that constitute the main girders to the position of the bridge bearing. So I create a point constraint from the top of the section to its bottom. Same thing on the right side.
Okay, now we can create the bridge bearings. So, as you can see, the bridge bearings are designed as a set of axial and torsional springs. And what I would like to do is to define these bearings as elastomeric bearings with an axial stiffness in horizontal direction of approximately 10,000 kilonewton per meter. So that's what I set here. The vertical direction I want to have very stiff. That's already inserted here. Okay, so I can now create the bearings. As you can see, these bearings, they have assigned an R set, which basically relates these individual springs to one another. And it is important that for each individual bearing I assign an individual R set number. So keep this in mind. We will do this later on, but now we will create the bearing. At the left position and now at the right one. Okay.
As next step, we will copy the bearing to the other end of the bridge. For this purpose, select the created elements of the bearing, so bearing itself and the couplings. Then right-click and select Copy with Base Point. Then select the base point, and now we can go to the bearing at the other end, so at s equals 32 meters, and insert, for example, with Ctrl V, and then select, of course, the same position of the base point as previously. Okay, now, as you can see, we have copied our bearing. Now, as mentioned, I should apply a different RSet number here. So I will choose Edit RSet and give it a new number. Now I will use 21 and apply this to all springs. Yeah, you can see how the number changes. I confirm with OK. Same for the right bearing. Here using B22. OK. OK. Okay, next we will go to the inner support. So once again, I copy this with the base point to the placement at s equals 16 meters. Ctrl V, I insert and adjust the RSet numbers. Here I will use E11 and E12. As you might remember from the introduction, we would like to also model a pier at the inner support. And for this, I first, of course, have to define the cross-section for the corresponding beam elements. So I close the cross-section editor and go back to cross-sections and insert a new standard section, rectangle, column. I adjust the dimensions, using a width of 4000 millimeters and a count height of 1000 millimeters. And I also define a new material for the pier, 20, standard concrete. And the same for the reinforcement. Okay. Then we go back to the cross members editor by clicking at the placement at the inner support. Now, first we delete the structural points that represent the fixed bottom of the bearings because we want to link them to the head of the pier. For this purpose, I draw a line between them and then draw the pier using the line command. So, okay, we'll use group 1. As element type, use centric beam. Select the correct cross section. Select start point and draw a pier with a height of 5 meters, for example. Now, of course, we have to define a structural point that represents the fixed support at the bottom of the pier. And still missing here, as you can see, is the link. I will delete this line here. It's the link between the bottom of the bearing and the head of the pier. And for that, we use once again point constraint and link the bearing to the head of the pier. Okay. Then we can close Cross Members Editor, take a look at the bridge, and now export SOFI Plus. Check how it looks like. Yeah, you can see. Orientation of the pier is still not like we want to have it. So we go back to SOFI Plus, select Align Elements, select the pier, and we want to rotate it around its local x-axis and use an angle of 90 degrees for that. Okay, let's export it once again. Yeah, that looks better now. Now we will go back to SOFI Plus to make the final adjustment in our model. And this is about design elements. In the present workflow, use design elements to define the structural member for which we want to do the design checks. So basically, we will define one design element for one of the bridge girders. So what I do here, I go to design elements, then select that I would like to have no prescribed cross-section because we want to take the cross-section from the already existing beam elements along the structural lines. So this is what I select here as collection method. I will scale up the maximum element length a bit to get not too many sections along the design element and keep the report a bit more compact. And as type of design element, I choose composite bridge girder. And this is a prerequisite for the checks we will do later with module composite. And the idea is that here, if you have selected this design element type, it will already be checked if the cross sections that are found for the design element are typically composite cross sections that can be used in the design process later on. Okay, that's about the background. Now let's create the element. For that, I will use the segment on axis option. Select an axis. And now I would like to create one design element over the complete bridge length. For this, I use the option to create one element between two placements and select the start and end placement of the bridge. And yeah, as you can see now, the design element has been created. Here in green. Now, what I would also like to do is that I will create two sections measured from the start at 15.99 and 1601 meters, so slightly before and after the inner support, to get for the design checks really a section left and right of the inner support, as of course we will have other shear forces, for example, there. Okay, and that's it. We have our model fully created. I export once again. And we will take a final look in the decreator. So we have everything we need. Girders, slab, pier, bearings. And as next step, we will create the loads on this structure. So see you in the next video.